Two videos in this series, areas as summation and integration as the reverse of differentiation, have shown that the area under a curve above the x-axis and between two ordinates, that's two values of x, can be calculated by using integration. And what we want to do is develop that idea and look at some more examples of that in this particular video. So, let's begin by exploring the question. If we've got the function y equals x times x minus 1 times x minus 2, what's the area contained between this curve and the x-axis? Well, the very nature of the question suggests, hang on a minute, there might be something a bit odd here. Let's draw a picture. So let's start by sketching this curve. Well, if we put y equals 0, then we can see that each one of these brackets could be 0. And that will give us a series of points on the curve. So if y is 0, then this could be 0, i.e. x could be 0. Or x minus 1 could be 0, in other words, x could be equal to 1. Or x minus 2 could be 0, in other words, x could be equal to 2. So there on the x-axis, I know that this curve is going to go through there, and through there. What about when x is very large? What's going to happen to y? Well, when x is very large, x minus 1, x minus 2 are really very similar to x. So effectively, we've got x times by x times by x. In other words, if x is very large and positive, so must y be. So we've got a bit of curve there. Similarly, if x is large but negative, again, taking 1 off and taking 2 off isn't going to make a great deal of difference. So we've got a large negative number times by a large negative number times by a large negative number. The answer is going to be very large but negative, because with 3 negative numbers multiplied together. So there's a bit of a curve down here. Now, how can we join that up? Well, assuming the curve is continuous, it's going to go up, over, down, and back up again. So that's the picture of our curve. And straight away we can see what the question is asking us. Find the area contained by the curve and the x-axis. It wants these two areas. But they're in different positions. One, area A, is above the x-axis, and the other one, area B, is below the x-axis. So perhaps we'd better be cautious and work out these two areas separately. Now, what we've been told, what we know, is that if we integrate between the limits, so in this case that's 0 and 1, our function, that's x times by x minus 1 times by x minus 2, with respect to x, we will get this area A. So the area A is equal to the result of carrying out this integration and substituting in the limits of integration. So let's do that. First of all, we will need to multiply out these brackets. Well, x times by x is x squared, and times by that x again is x cubed. I've got x times by minus 2 gives me minus 2x, and minus 1 times by x gives me another minus x. So altogether I've got minus 3x coming out of these brackets, and I need to times it by x, so that's minus 3x squared. Then I've got minus 1 times by minus 2, that's plus 2, and I need to times that by x, so that's plus 2x, to be integrated with respect to x. So let's carry out the integration. Remember, we had 1 to the index and divide by the new index. So that's 1 to the index makes that x to the power 4 divided by 4, minus 3 To integrate x squared, we add 1 to the index, that's x cubed, divided by the new index, that's 3, plus 2x. Now, x is x to the power 1. We don't always write the 1 there, but we know that it means x to the power 1. So we add 1 to the index, that's x squared, and we divide by the new index. And these are our limits of integration, 0 and 1. We can do a little bit of simplifying in here. We can cancel a 3 with a 3 and a 2 with a 2. And now we can put in our limit of integration, the top one, put 1 in. So that's x to the power 4 when x is 1 is just 1 over 4, minus x cubed when x is 1, so that's just 1, plus x squared when x is 1, so that's just 1 again. Minus, and now we substitute in our lower limit, that's 0, but when we put 0 in there, that's 0, and that's 0 as well, and that's 0 as well, because x is equal to 0 in each case. So the whole of the second bracket here is just 0. So when we simplify that, we get a quarter. So the area A is a quarter of a unit of area. What about area B? We can find that by doing the same integration, and this time taking the limits between 1 and 2. So let's look at that one. B will be the integral between 1 and 2 of x cubed minus 3x squared plus 2x with respect to x. So, let's have a look what we're going to get. The integral of this should not be any different to what we had last time. So if we integrate the x cubed, we have x to the 4th over 4 minus 3x cubed over 3 plus 2x squared over 2, and this is to be evaluated at the limits 1 and 2. And again, we can cancel the 3's and we can cancel the 2's. So now let's substitute in our upper limit. X to the power 4 when x is 2. So that's 2 multiplied by itself 4 times. And that gives us 16 over 4. Minus x cubed, which is 2 multiplied by itself 3 times. So that's 8. Plus x squared, which is 2 multiplied by itself twice. So that's 4. Minus, and now we put the 1 in, so that's a quarter, because x to the power 4 is just 1. Minus 1, because x cubed is just 1 when x is 1. Plus 1. Now let's simplify each of these brackets separately. 4 into 16 goes 4 times. So with 4 take away 8 plus 4. Well, that bracket is now 0. Minus, well, with a quarter take away 1, add 1. So this bracket is just a quarter. So our answer is minus a quarter. Let's just have a look where B was. B is here. It's underneath the x-axis. Now, if you remember, or if you look back at the video on integration as summation, one of the things that we were looking at when we had a piece of curve, and we were looking at the area underneath that curve, we took small strips. And these small strips were of height y and thickness delta x. And so the little bit of area that they represented, delta A, was y times by delta x. Now that's fine for what we've done, but notice this y is positive. And so when we add up all these strips that are above the x-axis, we get a positive answer, i.e. for A, the answer we got was a quarter. But for B, these y values are actually below the x-axis. And so this area, in a sense, is a negative area because the y's are negative. Hence, our answer is minus a quarter. But the question said, what is the area? And clearly, physically, there are two blocks of area. And so the total area must be a quarter, that's the area of that, and a quarter, because a quarter is the area of that. The minus sign merely tells us it's below the x-axis. So the answer to our original question, what's the area that that's contained between the curve and the x-axis, is given by the area is a quarter plus a quarter, which is a half. Let's just check on something. What would happen if we took the integral of our function between 0 and 2? Let's remember what our function is. It's x cubed minus 3x squared plus 2x integrated with respect to x. So let's do that integration. And again, the answer shouldn't be any different from what we've had before. X to the 4th over 4 minus 3x cubed over 3 plus 2x squared over 2 to be evaluated between 0 and 2. And again, we can do the cancelling. The 3's there and the 2's there. Equals. Let's substitute in the upper limit. So that's x to the power 4 when x is 2. 2 multiplied by itself 4 times is 16, and to be divided by 4. Minus x cubed minus 2 multiplied by itself 3 times, that's 8. Plus x squared, that's 2 multiplied by itself twice, so that's plus 4. Minus, and when we put 0 in, that's 0, and that one's 0. So the whole of that bracket is 0. Cancelling here, this leaves us with a 4, and so we have 0 minus 0 is 0. Which is what we would expect, because in a sense what this process has done is added together the two areas that we got with respect to their signs. A quarter plus minus a quarter is 0. What that means is that we have to be very, very careful when we're calculating areas. Clearly, if we just integrated between the given limits, what we might do is end up with an answer that is the value of the integral and not the area. And what this example shows us is that the area that is contained by our function, the x-axis and specific values of the ordinates, i.e. values of x, may not be the same as the value of the integral. So bearing that in mind, let's have a look at some more examples. This time, let's take function, or the curve, y equals x times by x minus 3, and let's investigate what's the area contained by the curve, the x-axis, and the ordinates x equals 0 and x equals 5. Well, from what we've learned so far, one of the things we've got to do is a sketch. So here's our x and y axes. If we set y equals 0, then we can see that either x is 0 or x can be equal to 3. So that gives us 2 points on the curve, there at the origin and there where x equals 3. We also know that we're going up to x equals 5, so let's mark that there. When we multiply out this bracket, we can see we've got x times by x gives us x squared, and it's a positive x squared, which means that it's going to be a U shape coming down like that. Now it wants the area between the x-axis, the curve, and these ordinates. So let's draw that in there. And again we can see we've got two lots of area. An area A, which is below the x-axis, and an area B, which is above it. This means we've got to be careful and work out each area separately. So the area A is the integral between 0 and 3 of x times by x minus 3 with respect to x. Let's multiply out the brackets first. So x times by x gives us x squared. X times by minus 3 gives us minus 3x. And we're integrating that with respect to x. So let's do the integration. X squared integrates to x cubed over 3. Add 1 to the index and divide by that new index. Minus 3x. This is x to the power 1. Add 1 to the index and divide by the new index. And that's to be evaluated between 0 and 3. Equals. We put the upper limit in first. X cubed. X is equal to 3, so this is 3 cubed. That's 27 over 3. Minus 3 times by x squared. And x is 3, so we have minus 3 times by 9 is 27 over 2. Minus, now we put the lower limit in, x cubed is 0 when x is 0, and x squared is 0 when x is 0. So that is minus 0. Equals, so now we've got 27 over 3 minus 27 over 2. We can cancel by the 3 here. That's 9. So we have 9 minus, and 2's into 27 go 13 and a half. That will simplify to that. And so we have minus 4 and a half. So that's the area A. Let's now have a look at the area B. So that's the integral of x squared minus 3x with respect to x, this time between 3 and 5. We'll get exactly the same as we've got here because we're integrating exactly the same function. But the limits are different. They're between 3 and 5. So let's turn over the page. The area B is equal to, let's remember that it's this that we are evaluating. Between 3 and 5. So we put in our upper limit first. X cubed, when x is equal to 5, is 5 multiplied by itself 3 times, and that's 125 over 3. Minus x squared, when x is 5, that's 5 times by 5 is 25. 25 times by 3 is 75 over 2. And that's our first bracket. Minus, and now we put in the 3. So that's 27 over 3. because if you think about it, we've actually worked this out before, minus x is 3, 3 squared is 9, times by that is 27 over 2. OK. Let's tidy up these bits first. 125 over 3 minus 27 over 3, well, that's 98 over 3. Minus, now I have minus 75 over 2 minus 27 over 2. So I've got minus 75 plus 27. And that is going to give me 48 over 2. So if you divide by 3 there, 3's into 9 goes 3, and 3's into 8 goes 2, and there are 2 overs, that's 32 and 2/3, minus 2's into 48 goes 24. So the area B is 32 and 2/3 minus 24, that's 8 and 2/3. So the actual area that I've got is the area of A, the actual area of A, which is 4.5. The minus sign tells us that it's below the x-axis. 4.5 plus the area of B, which is 8 and 2/3. Now, if I want to add 1/2 and 2/3 together, then they've really got to be in terms of the same denominator. So the 4 and the 8 gives me 12 plus 1/2. Now the denominator is going to be 6, so that's 3/6 plus 4/6, which is what the 2/3 is equal to. I've got 7/6 here, which is 1 and a 6. That's 13 and a 6 is the actual value of my area. Let's take another example. This time, let's have a look at the function y is equal to x squared plus x plus 4. Now, if we set y equals 0, then we're trying to solve this equation, x squared plus x plus 4 equals 0, to find where the curve crosses the x-axis. Doesn't look very promising. Everything here looks sort of positive, got plus terms in it. Let's check b squared minus 4ac. Remember, the formula for solving a quadratic equation is x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. But it's this bit that's the important bit, the b squared minus 4ac. Because if that's negative, i.e. when we take a square root, we can't have the square root of a negative number, what that tells us is that this equation has no roots. So b squared, well, there's 1x, so b is equal to 1, so that's 1 squared minus 4 times a. Well, a is 1, because there's 1x squared, and c is 4. Well, that's 1 minus 16 is minus 15. It's less than 0. There are no roots for this equation, so it doesn't meet the x-axis. So let's have a look at a picture for that. There's the x-axis, the y-axis. I'd like to be able to fix a point on the curve, and I can by taking x is 0. Those two terms would be 0, so that gives me y equals 4. So that's a point on the curve. But it's always going to be above the x-axis. And because x squared is positive, whether x is positive or negative, x squared is always going to be positive. So it's always going to be that way up. And it's going to look something like that. So we want the area between this curve, the x-axis, and the ordinates x equals 1 and x equals 3. X equals 1, let's say, is there. x equals 3, let's say, is there. That's the area that we're after. No real problems with that area. So let's do the calculation. The area is equal to the integral between 1 and 3 of x squared plus x plus 4 with respect to x. Integrating each of these, add 1 to the index and divide by the new index. Same again there. And then 4 is 4x when we integrate it. And this is to be evaluated between 1 and 3. So let's just turn this over. Remember, the area that we're wanting is equal to, this is what we have to work out, x cubed over 3 plus x squared over 2 plus 4x, and that's to be evaluated between 1 and 3. So we put the upper limit in first. So when x is equal to 3, 3 cubed is equal to 27 over 3 plus x squared, when x is equal to 3, that's 9 over 2 plus 4x, when x is equal to 3, that's 12. Now we put the lower limit in. So when x is 1, x cubed is 1, so that's 1 divided by 3, plus when x is 1, that's x squared is 1 and divided by 2, and when x is 1, that's plus 4. Now, some of these we can work out quite easily, but let's do the thirds bit first. We've 27 over 3, take away a third, is 26 over 3. We've 9 over 2, take away 1 over 2, so that's plus 8 over 2. And we've 12, take away 4, so that's plus 8. That will cancel down to there. If I do 3's into 26, 8 3's are 24 and 2 over, so that's 2/3, plus 4 and 8 is 12. So altogether that's an area of 20 and 2/3. Now, we can work out the area between a curve, the x-axis, and some given values of x, the ordinates. We can extend this technique, though, to working out the area contained between two curves. Let's have a look at that. Supposing you've got the curve y equals x times 3 minus x, and we've got the straight line y equals x. And we say, what's the area that's contained between these two curves? Well, let's have a look at a picture just to see what that looks like. If we set y equals 0 again, then that will give us the values of x where this curve crosses the x-axis. Clearly it does so there when x is 0 and also when x is equal to 3. We've also got x times by minus x gives us minus x squared. So for a quadratic it's going to be an upside down u. It's going to do that. Just missed that point. Let's make it a bit bigger so it goes through it. The line y equals x, well, that's a straight line going through there. And so the line crosses the curve at these 2 points. Let me call that one P, and this one is O, the origin. And the area that I'm interested in is this one in here, the area caught between the 2 curves. Well, before I can find that area, I really need to know what's this point P. Where do these 2 curves cross? Well, they will cross when their y values are equal. So they will intersect or meet when x times by 3 minus x is equal to x. Multiply out the bracket. 3x minus x squared is equal to x. Take x away from both sides. 2x minus x squared is then 0. This is a quadratic, and it factorises. There's a common factor of x in each term. So we can take that out, and we're left with 2 minus x equals 0. Either the x can be 0 or the 2 minus x can be 0, so therefore x is 0 or x equals 2. So this is where x is equal to 0, here at the origin. When x is 0, y is 0. So we put 0 in there, we have 0 times by 3 is nothing. If we put 0 in there, we get nothing. Or y is equal to, well, this says y equals x, so presumably y must be equal to 2. And let's just check it over here. If we put x equals 2, we've 2 times 3 minus 2. 3 minus 2 is 1, times by 2 is 2. So it's this here that's the point P. So let's just put that in, 2 there. Now this is the area that we want. So we can look at it as finding the area under the curve between 0 and 2 and finding the area under the straight line and then subtracting them in order to end up with that. So let's do that. Let's first of all find the area under the curve. Equals. Now this will be the integral between 0 and 2 of our curve. X times by 3 minus x. With respect to x. So let's first of all multiply out the bracket. X times by 3 is 3x. X times by minus x is minus x squared dx. Do the integration. Integral of x is x squared over 2. And we need to multiply it by the 3 that we've got there. And then the integral of x squared is going to be x cubed over 3. That to be evaluated between 0 and 2. So we put the 2 in first. So we've 3 times 2 2's are 4, and to be divided by 2, minus x cubed over 3. X is 2, so that's 8 over 3, minus, and when we put the 0 in, x squared is 0 and x cubed is 0. So that second bracket is 0. Equals, well, we can cancel a 2 there. So 3 2's are 6, minus 3's into 8 goes 2, and there's 2 over, so that's 2/3. So the area that we've got is 6 minus 2 2/3, which is 3 1/3. So that's the area under the curve. What now we need is the area under y equals x. So this will be equal to the integral between 0 and 2 of x dx equals integral of x is just x squared over 2 between 0 and 2. Substitute in the 2. 2 2's are 4 over 2. Minus, put the 0 in, and the x squared over 2 gives us 0. And so we've just got 2. 2's into 4 goes 2, nothing there. So here we've got the area under the curve, 3 1/3. Here we've got the area under y equals x, 2. And so the area between them let's look at their positions. We've calculated this area here under the curve. That's the one that is 3 1/3. And we've calculated the area of this bit of triangle that's here underneath y equals x, and the answer to that is 2. And so what we're looking for is the difference between the big area and the triangle. So that's 3 1/3 minus 2 gives us 1 1/3. So we've seen how we can extend the technique of finding the area under a curve between the x-axis and between two given ordinates to finding the area between two given curves. Let's take another example. This time let's use the function y equals sine x. We'd better define a range of values of x, so I'm going to take x to be between 0 and pi. And let's say I want the area that's cut off from that by the line y equals 1 over root 2. So, a little sketch, as always. When we're finding these areas, it's important to know where they are. So, y equals sine x between 0 and pi. So, it's going to look like that. And there's pi, and there's 0. And y is equal to 1 over root 2. Well, that's a straight line, somewhere, let's say, across there. So this is the area that we're after, the area between the line and that curve. What we need to know, what are these values of x? Well, y is equal to 1 over root 2 and y is equal to sine x. So 1 over root 2 is equal to sine x where they meet. So the values of x will be the solutions to this equation. Well, one of the values we do know is that when sine x equals 1 over root 2, x must be equal to pi over 4. We're working in radians, so I've got to give the answer in radians, but the equivalent answer in degrees is 45. So that's that one there, and the one there is 3 pi over 4. So now I can work out what it is I've got to do. I can find the area under the sine curve between these two values, and I can find the area of this rectangle and take it away. And that will leave me that area there. Just let me put these answers in that I found there and there. So let's first of all find the area under this curve. So the area under the curve is equal to the integral between pi by 4 and 3 pi by 4 of sine x dx equal. So I have to integrate sine x. Well, the integral of sine x is minus cos x. And we have to evaluate that between pi by 4 and 3 pi by 4. So we put in the upper limit first, minus the cos of 3 pi by 4, that's the first bracket, minus the cos of pi by 4. Now, cos of 3 pi by 4 is minus 1 over root 2, and that minus sign gives me plus 1 over root 2. The cos of pi by 4 is 1 over root 2. Minus minus gives me plus 1 over root 2. So that is 2 over root 2, which is just root 2. So I now know this area here. What I need to do is calculate the area of this rectangle. Then I can take it away from that. Well, it is a rectangle. Its height is 1 over root 2. So area equals 1 over root 2, that's the height of that rectangle, times by this base, its width. Well, it runs from pi by 4 to 3 pi by 4. So the difference is 2 pi by 4. In other words, pi by 2. So the area of that rectangle is pi over 2 times root 2. So the total area that I want is the difference between these two, pi over 2 root 2 and root 2. So the area equals root 2 minus pi over 2 root 2. And put all that over a common denominator of 2 root 2, which makes this 4 minus pi. And I think we'll leave that as that. And that's the area that's contained in there between the straight line and the curve. I want now just to go back to the example where we were looking at the area that was between these two curves. If you remember, we had this sketch of the curve. So that was the picture that we had. And we calculated the area between the two curves here by finding the area underneath x times by 3 minus x, then the area underneath the line y equals x, and taking them away. Another way of looking at this might be to go back to first principles. If you remember, when we did that, we took little rectangular strips, which were roughly of height y and thickness delta x. Well, couldn't we do the same here? Have little rectangular strips, well, they're not quite rectangles, but they are thin strips, and their y bit, so to speak, would be the difference between these two values of y here. So if we were to call this y1, let's say, and this one y2, then might not the area that we're looking for, the area between these two curves, y1 and y2, between these ordinates here, let's call them A and B, might not we be able to work it out by doing that? In other words, take the upper curve and call it y1, take the lower curve and call it y2, subtract them, and then integrate between the required limits. Well, let's see if this will give us the same answer as we had in the previous case. So our limits here are 0 to 2, and y1 is this one. Let's multiply it out first. X times by 3 is 3x, and x times by minus x is minus x squared. Take away y2, so we're taking away x and integrating with respect to x. So I have 2x minus x, 3x minus x. That gives us 2x minus x squared to be evaluated between 0 and 2 with respect to x. So let's carry out this integration. The integral of x is x squared over 2, so that's 2 times x squared over 2. The integral of x squared is x cubed over 3, between 0 and 2. I can cancel a 2 there and there, substitute in. 2 2's are 4, minus x cubed, when x is 2, that's 8 over 3, minus, and when I put 0 in, that second bracket is just 0, equals 4 minus 2 and 2/3, which just gives me 1 1/3 units of area, which is exactly what we had last time. So this gives us a convenient formula for being able to work out the area that is caught between two curves. We call the upper curve y1, the lower curve y2, and we subtract them and then integrate between the ordinates of the points of intersection.